Here we're given a second-order homogeneous differential equation with initial conditions. We're asked to apply the Laplace transform and solve for big Y of s, which equals the Laplace transform of y, and then we want to solve the initial value problem by using the inverse Laplace transform, which will give us y of t, where y of t equals the inverse Laplace transform of big Y of s. So our first step is to take the Laplace transform of both sides of the differential equation, which would give us the Laplace transform of y double prime minus 10y prime plus 25y equals the Laplace transform of 0. And now we use linearity, or the properties of Laplace transforms, and rewrite the left side. We'll write the left side as the Laplace transform of y double prime minus 10 times the Laplace transform of y prime plus 25 times the Laplace transform of y equals the Laplace transform of 0. And now we know the Laplace transform of y double prime equals s squared times big Y of s minus s times y of 0 minus y prime of 0. Then we have minus 10 times the Laplace transform of y prime, so we'd have minus 10 times the quantity. The Laplace transform of y prime equals s times big Y of s minus y of 0. Then we have plus 25 times the Laplace transform of y, which will give us plus 25 times big Y of s equals the Laplace transform of 0 is 0. Now let's clear the parentheses here by distributing. The other terms will remain the same. So we'll have minus 10s big Y of s plus 10 y of 0, and then we have plus 25 big Y of s equals 0. For our next step, we'll use the initial conditions and substitute 2 for y of 0 and negative 1 for y prime of 0. So we'll substitute 2 here and here, and we'll substitute negative 1 here. So that would give us s squared big Y of s, and then we'll have minus s times 2, so minus 2s. Here we'll have minus negative 1, which would be plus 1, and minus 10s big Y of s, and then plus 10 times 2, so we have plus 20, plus 25 big Y of s equals 0. Notice how we have three terms that have a factor of big Y of s, here, here, and here. So for our next step, we'll factor out big Y of s from these three terms and move the remaining terms to the right side of the equation. So that would give us big Y of s times the quantity s squared minus 10s plus 25 equals, we'd add 2s to both sides, so we'd have 2s, and then notice that 1 plus 20 is 21, so we subtract 21 on both sides, so the right side of the equation is 2s minus 21. And now let's continue on the next slide. To solve for big Y of s, we'll divide both sides by the quantity s squared minus 10s plus 25. Simplifying, we now know the Laplace transform of y, or big Y of s, equals the quantity 2s minus 21 divided by the quantity s squared minus 10s plus 25. Notice how if we wanted to, we could factor the denominator. This is a perfect square trinomial, so we'd have the quantity 2s minus 21 divided by the quantity, we'd have two binomial factors, or the factors of s squared are s and s, and the factors of 25 that add to negative 10 are negative 5 and negative 5. So notice how we can write the denominator as the quantity s minus 5 squared. Our question does ask for big Y of s, which we can enter in this form or this form. I'm going to go ahead and enter this form here. Again, big Y of s equals quantity 2s minus 21 divided by the quantity s squared minus 10s plus 25. Now we actually want to solve the initial value problem by determining little y of t by finding the inverse Laplace transform of big Y of s. However, before we do this, we do want to perform partial fraction decomposition on this fraction here, so we can use a table of Laplace transforms in order to find the inverse Laplace transform. Let's go ahead and perform partial fraction decomposition on this fraction here. So we have the quantity 2s minus 21 divided by the quantity s minus 5 squared. And notice how we have two linear factors here. So we'll have a sum of two fractions, where we'll first have a divided by one factor of s minus 5. And then because this linear factor is repeated, we'll have plus b divided by the quantity s minus 5 squared. And now we'll form the basic equation by multiplying both sides by the quantity s minus 5 squared. Well, that would give us the equation 2s minus 21 equals, when multiplying the square of s minus 5 times this fraction, one factor of s minus 5 would simplify out, giving us a times the quantity s minus 5. And when multiplying the quantity s minus 5 squared and this fraction, both factors of s minus 5 would simplify out, giving us just plus b. And now we'll select convenient values of s in order to find the values of a and b, so we can write big Y of s as a sum of these two fractions. So let's let s equal 5, because that would make this factor 0. So if s is 5, here we'd have 2 times 5 minus 21, that's negative 11, equals, this would be 0, and therefore we just have b. So we know b must equal negative 11. And now we'll select another value of s to determine the value of a. Let's select s equals 0. So if s equals 0, we'd have the equation negative 21 equals, if s is 0, this would be negative 5a and then plus b. But we know b equals negative 11. So we'd have negative 21 equals negative 5a minus 11. Adding 11 to both sides, we'd have negative 10 equals negative 5a, so a equals positive 2. So using the values of a and b, we can now write big Y of s as a sum of two fractions. Big Y of s is equal to, a is positive 2, so we'd have 2 divided by the quantity s minus 5. And then because b is negative, we'd have minus 11 divided by the quantity s minus 5 squared. So now to find the inverse Laplace transform of big Y of s, which will give us y of t, we'll take the inverse Laplace transform of both sides of this equation. And let's do this on the next slide. We'd have the inverse Laplace transform of big Y of s equals the inverse Laplace transform of 2 divided by the quantity s minus 5 minus 11 divided by the quantity s minus 5 squared. Well, we know the inverse Laplace transform of big Y of s is y of t, which is what we're looking for. So we have y of t equals, let's rewrite the right side using properties of inverse Laplace transforms as 2 times the inverse Laplace transform of, because we factored out the 2, this would now be 1 over the quantity s minus 5, and then minus 11 times the inverse Laplace transform of 1 over the quantity s minus 5 squared. Now let's look at the table of Laplace transforms below. Notice how the second column has big F of s, in our case big Y of s, and the first column is f of t, which in our case would be y of t. So because we're determining inverse Laplace transforms, we'll be using this table in this direction here. Looking at this column, let's see if we can find a form that fits this inverse Laplace transform. Notice how here we have 1 over the quantity s minus a, which fits this form perfectly, where a is equal to positive 5, which means this inverse Laplace transform is e raised to the power of 5t. So we know that y of t equals 2 times e raised to the power of 5t. Now looking at this inverse Laplace transform, because the denominator is the quantity s minus 5 squared, notice how it fits this last form here, where the denominator is in the form of the quantity s minus a raised to the power of n plus 1. So because this is squared, that means n would have to be 1, since 1 plus 1 is 2, and therefore the numerator must be 1 factorial, which equals 1 which we have, and therefore this fits the form perfectly, again where n equals 1, and therefore the inverse Laplace transform is t to the first times e raised to the power of 5t. So our second term here is minus 11t e to the 5t. So this is our solution to the initial value problem. If we wanted to, we could factor out the common factor of e raised to the power of 5t and write this as y of t equals e to the 5t times the quantity 2 minus 11t. Either of these two forms are acceptable. So going back to our first slide, again we have y of t equals 2 e to the 5t minus 11t e to the 5t. I'm not sure if you noticed, but we could have found this particular solution much faster by using a characteristic equation where we'd have a repeated root or repeated solution. I hope you found this helpful.